Today I'm going to demo DICOM image processing in Greenplum. DICOM images are medical X-ray images, mostly in grayscale format. Um, so yeah. So before we get into specifics of DICOM image processing, I wanted to introduce Greenplum database with GPUs and containers. The architecture of Greenplum database with GPUs and containers in it. So basically, as you see in this slide, Greenplum master node is there, and then there are segment hosts which are physical servers that are there. Let's say you have four segment servers, like segment one, host 1, 2, 3, and 4. And due to cost reasons, you can have GPUs on only two segments, and then remaining two can be running on CPUs. So of course, I mean all of them will have CPUs, but GPUs are attached only to two segment hosts, and training, I mean deep learning, distributed deep learning training will happen only on those two segment hosts. So, or you can have GPUs attached to all of the segment hosts if you can procure them, like all the four segment hosts can be attached to GPUs. So it is like up to the customer, whether you want to have GPUs on only two nodes or all of the nodes, or like three nodes, something like that. So once GPUs are attached to it, Greenplum can take advantage of GPUs and do distributed deep learning of images, text data, all of that. And on top of it, not only GPUs, like Greenplum has evolved with PL containers, like Docker engine is running on each segment host, and the whatever PL Python code that we write, you can containerize the code and then run it as a container in each segment host in distributed and parallel fashion. So previously it used to be PL Python, like still we have PL Python functionality. It is like PL container is like an extension to PL Python, where you containerize the Python code or R code or Java code, whatever it is, the language. You containerize it and to run in distributed and parallel manner. So this is the overall architecture of Greenplum database with GPUs and container. So as you can see, like you can interact with Greenplum with SQL or PL Python or PLR or PL container. So the next thing is um, like a broader architecture of DICOM image processing and Greenplum. So basically, the images can be in AWS3, or they can reside on a hard drive. Like it can be a network drive attached to Greenplum, like where Greenplum can access that network drive, or the images, if they are like let's say 20,000 something like that, not in millions, then they can reside on the master node itself. But you can have it on a drive which is network connected to Greenplum master node. So, or you can completely put it on a cloud S3, I mean our AWS S3 server, like all the images on there. So basically, so let's say if you have the DCM images on the hard drive, then you take these DCM images, convert it into byte array format, or each DICOM, like DICOM images are comes with an extension .dcm. So you convert them to byte array format, and then write it to a single txt file, and then load it into Greenplum. Like the single txt file is loaded in parallel way using Greenplum native load command support, and then you load it into master, you load it into Greenplum. So the images will be loaded, the byte array format images will be loaded into a table across all the segment hosts. So once you do that, so if it is on S3 or AWS S3, you don't have to do this byte array conversion and all that. You can directly read the S3 as such. So once the data is available, right, the DICOM images are available on in the byte array format on all the segment hosts. Um, then you can use PL Python or PL container functionality to extract patient's metadata and image pixel array data from the DCM images. So we have loaded the images, DICOM images as is in byte array format. Now you can take the patient's, but we have to extract the patient's metadata and image data. The image data is buried inside that DCM images. So we have to extract them, like patient's metadata and image pixel data from DICOM images, then load it into another table where you have all the patient's metadata as well as the image data, like the NumPy array format, like that will be there. So that part is the first step that we do. Once we do that, so we have the image data in a NumPy array format that is available there. Then you take that, split the data into train and validation set, so that you build the model and training set, and then test your model accuracy or AEC on the validation set. So this is all the green boxes are Madlib functionality. Madlib is a framework available within Greenplum, which does parallel and distributed machine learning and deep learning possible. So then after you do the train and validation set splitting, right, you take the train and validation images and pack and distribute them into segment servers. Like, so let's say in the beginning we have discussed, right, I mean there are four segment servers, and you only have GPUs attached to two segment servers. So in that case we want to put only the images onto those two segment servers, right, that has GPUs connected to it. So this third step, what it does is it takes all of the image data that is there, the DICOM image data, distributes only to those two segment host where GPUs are attached. Let's say if you have GPUs on all the four segment servers, then it will equally distribute them into all four segment hosts. So that uh, packing of images and distribution of images is done in step 3. Then once we have that, step 4 is like you can define and load deep learning model architecture. Like you can use any of the model architectures. There are so many of them. Like AlexNet is lighter and faster. You can use ResNet, ExceptionNet, whatever it is. Like you can use a lot of net image processing, deep learning architectures. You define them and then load it into Greenplum using Madlib functions. Then once you load that architecture into Flow, then what we do is using Madlib fit functions, you fit the data to the architecture that you have defined. So once you do that, it goes for an iteration. We'll talk about the performance metrics of that. So yeah, once you trained model is trained, so you take the trained model and score, predict the train validation set using the trained model. So basically, the whatever example data set we have taken is like 26,000 images, where each image has whether the patient has pneumonia or not. So pneumonia or no pneumonia. So it's a 1-0 classification. So we have patients data with pneumonia and patients images without pneumonia. So you train it on both of them. Then the validation set will have 221 images which the model doesn't see, and it will be able to tell whether the patient has pneumonia or not based on the DICOM image. So that's the sixth step. Then we compute the AUC, because there is a high class imbalance in the data set that we have taken. Like 78% of rows are like no pneumonia, and 22% are with pneumonia. So it's a very high class imbalance. So we compute the AUC area under the curve, and the model it was able to predict with 0.75 because we just took AlexNet and then did a because it's lighter and faster. But then if you take ResNet, ExceptionNet like that, you can even push it to 0.95 AUC. So that's the set of functions that we execute. Everything, whatever you're seeing in this slide, is distributed and parallel. So we'll see the performance metrics here. So in this slide, if you see like performance metrics comparison between Greenplum distributed GPU training versus single GPU system training. So the advantage of Greenplum is like you can load 30 different models. So the 30 is an arbitrary number what I taken, but you can take X number of different model configurations, changing hyperparameters, model architectures, batch sizes, all that, hyperparameters, model architectures. Once you change it, there will be a huge number of configurations that will generate. So we can Madlib will generate all of these different configurations. Once we have these configurations, you can try out all of these configurations on the set of images. You see here the thing that we have done. Greenplum on 26,463 images ran through 75 times on all of the images on 4 GPUs attached to the 4 segment hosts, and there are 30 different models it has trained in 8 hours, just 8 hours. Whereas standalone, if you take single GPU system, it's 26,463 images, 75 passes over the images, 1 GPU attached to the just 1 GPU, right? Single GPU system, it's not distributed processing, and one model, not one model. So it's 26K images, 75 epochs, same number of epochs, 1 GPU because it is standalone, not distributed. Then one model took 1 hour and 18 minutes. So if you scale out, right, like if you not scale out, if you compute, so the same for if you have to do try out for 30 models, right? I have to do for 30 models, it would take 35.4 hours. Whereas we have taken only 8 hours to do the same because it is distributed in parallel computation. So it is like an advantage of 5 times faster. So it is not just having 5 times faster. It is like you are able to try out 30 different models in just a span of 8 hours. So that gives an edge to the data scientist, to try out more, to do more experiments and churn out the results faster compared to the standalone or single GPU systems or some other thing like that. And if you take the same, why I say it is not, and if you see that the same Greenplum, if I take 4 GPUs and one model, if I try just one model, but 4 GPUs distributed processing, 75 same epoch, same number of images, it takes 44 minutes. So it cuts down the time by non-linear fashion. So when I take 44 minutes for one model, right, then for 30 models it should have ideally taken 1310. It should have taken 22 hours, but it has completed in 8 hours. So it is cutting down in a non-linear fashion the time. So what I'm saying is, like, the more data, the more models you have to try out. Greenplum will be more performance optimistic. Like, uh, the more you give, the more load you give, the better it performs. So it's like that. Then yeah, this is a summary. DICOM images can be loaded and processed in Greenplum. DICOM images can be on AWS3 or network attached drives to Greenplum. And Greenplum can still process those images and distribute them in parallel. The images need not be pushed to master node. They can be where they are. But if you have very small number of images, like 26K images, something like that, then you can put them on the master node and we can distribute it to segment node. But if you have like millions of images, they can be where they are. You can still do it in parallel and distributed node. Distributed deep learning model training inference can happen on images using GPU, CPU, and then native Madlib and PL container frameworks. The data extraction from DICOM can be done using PLX or PL container framework. PLX here stands for PL Python, PLR, PL Java, something like that. So that's it. Thank you.